Okay, so we welcome our second speaker, Srijan Bharati from Princeton University, who's going to give us a recipe for imaging global and local solar internal magnetism.
Hello, am I audible? Okay. So, as the title says, it's a recipe. So I have not actually done an inversion for magnetic fields yet, but we are doing it currently. So I'm not going to show those results, but it looks very promising before I start off. Yeah. Okay, so just to start off, there are some motivational pictures here. The first one, as you all know, is essentially the workings of the solar dynamo, which shows the 11-year solar cycles if you do simulations. And in the middle is a small patch on the sun, which is essentially a sunspot. And on the right is something that I'm going to talk about in a bit. Those are numerically evaluated Slepian functions, and it's traditionally used in the geophysics community. I am in the geosciences department in Princeton, but I sort of work between the astrophysics, plasma, and geosciences, so I have the privilege of actually using a lot of classically well-defined techniques in terrestrial seismology and applying them to helioseismic methods. So the one thing that sort of drives me in terms of understanding what magnetic fields look like under the surface is the image in the center, which on one side has a simulation and on the other side has an observation. And the fact that they're so close, but yet we don't have a direct seismic imaging of what magnetic fields look like underneath is it's pretty interesting for me. And so if you've already guessed it, the left side is simulation from Matthias Rempel, and on the right are observations. All right. So a brief outline, I'm going to first talk about the normal modes of the sun, which are the tools that I will be using. Then I'll talk about the sensitivity kernels. Maybe most of you already know about it, but I'll still show a very dumbed down example using a coffee cup. And then I'll talk about these beasts that forms basically the whole point of my study, which are the Lorentz stress sensitivity kernels. And then finally, I'll extend the global picture to a local case, which is Cartesian mode coupling. And finally, I'll talk about how we can apply Slepian functions to make inversions much more reliable and stable. A very simplistic picture of Fourier transform, where you have a general 1D signal, and you can project that into frequency space, which forms the peaks in frequency. In a 1D, if you let's say pluck a string of a guitar, it'll oscillate in various modes as sinusoids or cosines. And if you just take one of these strings and wrap it around a sphere, is what we have for a spherical harmonic. Almost all of you know what it is, but just because I found a very nice visual demonstration to show that spherical harmonics are actually a complete basis in a 2D surface. So this is essentially adding up all the spherical harmonics to form the cosmic microwave background. And at some point, you'll see it just look like a very random patch. So these are perfect basis functions, at least for the global case. These are over-exaggerated pictures of how the sun might oscillate in its various modes. And on the left, you have the Dopplergram. And if you take that picture and if you decompose it into all the spherical harmonics, you will get a time series for each of the spherical harmonics. And then if you decompose this time series into a Fourier transform, a temporal Fourier transform, you'll get this classic picture of power spectrum and helioseismology. And this is like one picture which shows you, the sun is oscillating in various shapes with various frequency contents and different powers. So a very important concept in all of what I'm doing is the concept of mode coupling. So what this picture shows is sort of a visual representation of a more mathematical part of the study, which is if you have two modes, which are represented by the left and the right spherical harmonics, they usually feel a structure, which can be a perturbation such as rotation or density or magnetic fields. In my case, it's mainly magnetic fields. And depending on what are the geometric patterns of these three interacting spherical harmonics, they will either integrate to give you something which is non-zero or something which is zero. And these are just dependent on the geometry. So for the first case, as you see, if you just multiply these spheres and integrate in phi and theta, you will get something which is not canceling out across hemispheres. But for the other two cases, you see that in this case, for example, if you go from the theta equals 0 to 90 or 180, it's going to cancel itself out. And in this case, if you go around the equator, it's also going to cancel itself out. And these are manifested in terms of integrals of 3 spherical harmonics, which turn out to be these beasts called Wigner 3J symbols, and they have its own selection rules. And this was just a visual demonstration of how these things come about to couple a certain structure and feel that structure depending on which two modes we are utilizing to look at the solar interiors. So again, most of you perhaps know about what kernels are, but again, I will just introduce this. So let's say we have an observation which is given by f, that's like frequency, k is a kernel, and b for my case is the perturbation, which is magnetic fields. And so if you have a coffee cup, and now let's say you know exactly what it looks like inside, so you would have the perturbation, which is b, to be 0 because you know exactly what it is. And the sensitivity of that entire length is, let's say, constant. So it will not have any response in frequency if you put a drop on the surface, and if you observe it, you can predict the ripples exactly from theory. But now, let's say you put a layer of sugar in it. At that point, you're introducing a perturbation. You put another drop, and you'll see these ripples, but they will sort of differ from what you would expect. And that's because you have a perturbation in there. And then you put a layer of cream, let's say, at some point, and you'll have another layer of perturbation. But then usually what happens is the kernel is not the constant across depth. So maybe there's a cooler layer. So your kernel will start having a higher sensitivity near the surface, which is the case for the P modes that we'll be using. So in our case, the coffee cup, of course, is the sun. And any sort of linear inverse theory will look like this problem, where you have observations such as frequency splittings that's measured from the sun, and kernels, which just come out of the physics. And perturbations are what we want to invert for. In the case of rotation, which has been very well measured by helioseismology, the kernels have been very well known forever. And so we know them very well, as we have already seen in so many plots. But then, what about magnetic fields? So the main problem with magnetic fields has been that these kernels for a general 3D configuration hasn't been known until very recently. And one of the main reasons is that magnetic fields turn out to be perturbations in a second-rank tensor. And when you try to use that as a perturbation, you'll see that there are 6 independent components, and the mathematics is horrendous at some point. So I'll tell you how sort of we could get around that. But this is not to say that there hasn't been no studies along these lines. There have been dedicated efforts by Gustafsson, Zimbowski, and then a lot of studies by Callie and Hannah Schunker. But then in 2020, as the first paper in my PhD, we found the explicit analytical closed form expressions for these kernels. And we can use them for imaging a general 3D Lorentz stress tensor. The way to do that is just the standard stability treatment of imaged equations. You take the 4 equations. These are ideal imaged equations, by the way. And then you just do a linearization on them and end up with a force operator. We can use the force operator and build the potential field and potential energy, and we can see that you have contributions from all the candidates you would expect, which are the Alfvén waves, the 2 kinds of them, then sound waves, and pressure and current-driven modes. So these are essentially some of the theoretical underpinnings. And finally, I've been talking about how magnetic fields are not really the perturbations, but really the Lorentz stresses. And that's because you have the J cross B term. So you see, if you want to really invert for B, there are 2 B's in there, so you have to club them together somehow. And as soon as you do that, those are the magnetic Lorentz stresses, and that's what H is in the right panel. And this thing in yellow is essentially the kernel, and that's the second-rank tensor. So I guess that's mainly why it was not really well found until now. But since I belong, again, in the geosciences department, and people have been looking at these elasticity tensors forever now, and those are 4th-rank tensors, I think. So they have been using these things called generalized spherical harmonics. So a usual spherical harmonic is for decomposing a scalar on the surface of a sphere. A vector spherical harmonic is to decompose a vector. But now if you have a tensor, you of course need something which is slightly more sophisticated, and these are generalized spherical harmonics. And they have its own identities which make life very, very easy if you use them carefully. What I'm showing on the right, you don't need to really look at everything. we go into this basis which is given by E minus E0 and E plus. These are the generalized bases. But then I also show how you can get back from these plus, minus, and 0 mess into B theta, B phi, and BR on the left. So we have all these conversion rules as well. All right, so this is how it looks like, the kernels. And as expected, they are very, very dominated near the surface and then slowly die out in the interior. A nice part of this is that, yes, it's very shallow sensitive, but it still covers the near surface shear layer, which means that there is some hope of actually inverting for the global large-scale fields in the near surface shear layers. All right, I'm going to skip over that. A small demonstration over here where we have built a toy model inspired from some of the numbers that we find in terms of what could exist inside the sun, where near the surface we have a 10 Gauss field, and at the interior we have a 10 power 7, and in the tachocline it's around 10 power 5. I'm not saying that these are like exactly what's there, but I built a model where it's poloidal in the near the surface and it's toroidal in the interior, and somewhere in between it becomes a mixed field. And if we make the near surface field 10 times of what exists in the sun, or so we believe, then we see that for modes which are of lower angular degree, which is on the left, the increase is far less than the modes for which angular degrees are very high. And that's because the modes for which angular degrees are high, the kernels are much more sensitive near the surface. But for low angular degrees, it's sort of spread out in the entire interior. So if we compare these numbers that we sort of get from our toy model with what is observed, we see that, so in this plot, these are the even A coefficients in the solar minima. And you see that the line that goes through the forest of modes that's observed, that's from the second order corrections due to rotation. So it sort of feels like in a minima, the magnetic fields don't really play a huge role, because this is without using magnetic fields in the orange line. But then if we go to the maxima, you see there's a very clear mismatch between what we can explain through just accounting for rotation and what's actually coming out from observations. And the numbers that we have from my toy model is sort of in the ballpark of what you see on the left axis over there. So it's sort of a check that the kernels are not entirely off. All right, so that's where we are for the large-scale fields. And just sorry to go back once, but we are currently under the process of actually trying to see if we can reproduce that from using different dynamo models across solar cycles. So that's a forward problem. And the harder problem will come after that, which is the inverse problem, where we would do the inversions. So moving on to the local case, because we already covered the global. So if we take this global picture of modes and you sort of zoom in a lot, those will start looking like plane waves. So therefore, naturally, the natural choice of basis for the modes in a local patch is a plane wave as opposed to spherical harmonics. And on the left over here is an observation, and the yellow lines sort of demarcate the different supergranules. And what I'm trying to show here is that from the Dopplergrams, we can identify the mode amplitudes corresponding to a certain wave number. So K over here denotes the L and M, which were azimuthal and angular degrees in a sphere. But in this case, these are just like wave numbers in 2D. And we can cross-correlate one mode with another to end up with measurements which are called B coefficients. These are just some mathematical constructions, and the important part over here is that B coefficients encapture the information of perturbations, which is seen by the interaction of these two modes. All right. So let's say the B coefficients in a spatial domain looks like this picture on the left. And what you see here is that it's a circle essentially, right? So now let's take the example of the most important circular patches on the sun, which are sunspots. And we can decompose this in plane wave basis. But if we want to do that, then essentially it kind of looks like this, that these are like plane waves coming from all directions, and we are trying to resolve a circle using all these straight lines, which means that the number of straight lines you would need effectively to decompose this is quite large. And if you deal with inverse problem, you would always want to keep the number of model parameters as less as possible. Therefore, if we want to invert for a pattern which is circular, an optimal choice would be to use something which is a circle. Before I go into that, the global mode coupling inverse problem look like the first equation, and the local mode coupling problem looks like the second equation if we use plane waves. What you see here is that the observation, which is lambda kk prime, has a kk prime index. The h, which are Lorentz stress, has a q index, and q is related to k and k prime as through a certain selection rule, which just means that for every perturbation which is h, we have a certain set of k and k prime, which is a subset of all available modes. So let's say there are 1 million data points available to you, and you want to invert for wave numbers which are approximately of the order of 1,000, which are all these plane waves coming from all directions. And so for each of them, you would need 1,000 data points. So it's like severely under-constrained in terms of what is already available to you. But I went ahead and I tried to find these kernels for the local case using plane waves. And then we were very optimistic and we thought, all right, we'll go ahead with this and we'll have amazing inversions. But then because of the reason I told you, the inversions look pretty bad, which I'll show in a bit. And that sort of made us thinking that we should change the plane wave basis into something else. A small caveat before I move into the Slepian function is that, as Chris mentioned the other day, when we have the kernels for magnetic fields, you see the terms over here have some kernel weighted by some perturbation, kernel perturbation, and so on. The very first one, which I have highlighted over there, has a sound speed perturbation along with the horizontal part of the magnetic pressure. What this essentially means is that when we are trying to invert for sound speed, it's sort of corrupted with magnetic fields, and therefore there is no one unambiguous way to do this. And this, I think I've already talked about, but okay, so for local mode coupling, all these spheres get replaced by exponentials, which are plane waves, and that gives you this selection rule that I was talking about. So coming back to some visual pictures again, if we have a sunspot, and if we just look at the BR square, or the vertical magnetic field component in that, that's the picture in the spatial domain on the left, and in the frequency domain, that's what it looks like on the right. So according to the inverse problem, the way I explained to you before, let's say we want to infer a structure which is of wave number q1. That is given by, let's say, that square, white square in that plot. So you see that it's only going to be the wave numbers k prime minus k which satisfy that relation to give you q1 that will actually figure into the inverse problem for q1. Now, if we try to invert for q2, similarly, it would be another set of k prime minus k and so on. And this essentially means that if we stick to the plane wave basis, there would be many, many independent linear inverse problems. And there are various problems related to this. The first one is that, again, the number of data constraint per perturbation is far less than we would want or we have. And secondly, if you do inverse problems, you would know there is this thing called regularization that you have to do, and you would end up with this L curve. And if you have to look at 1,000 different L curves to find the needs, so it's just a pain. So yeah, we would need plenty of coffee. But then this is also sort of like, when you're just trying to look at these different inverse problems to image the same structure, it's like looking at different parts of an elephant but being blind. And so you would think that it's the tail is like a rope, or the trunk is like a snake, and so on. But what if we can combine them? So what if the first one was not that, but rather this equation, where the left side stays the same, where it is kk prime again. The kernels also have a kk prime, but the difference is that the perturbation does not have a wave number in it, which means that all perturbations will be collectively constrained by all the data that you have. So instead of each perturbation being constrained by 1,000 different data points, it will be constrained by a million, which increases the signal to noise by square root of the factor that you're gaining in that, which is a large number. So for a circular pattern, which I showed before, what if the basis function looks like this, or like that, or like that, or that? So just 4 basis functions, right? And then you can explain everything within that circular dashed domain that I've shown. And these are essentially the Slepian functions. So what we do here is that we build this ratio of, we say that what is this function that is optimally constrained within the script R in the physical space, and we divide that with the energy of the entire R2 space. And you find the stationary points belonging to that, and you end up with an eigenvalue problem, which gives you all these numerically defined eigenfunctions. And as I've shown you, the first one here, where lambda is almost 1, because it's entirely concentrated within R. That's what that is. The energy of the function in the patch divided by the energy in the entire space is 1. And then as we go lower in lambda, it just means that it starts leaking out ever so slightly. And up to 30, you see it's still pretty concentrated. So what I do is, I showed you this picture in one of the previous slides. I make a hand-drawn circle in a part where I think that my perturbation of interest exists. And then I do a deconstruction and reconstruction in the Slepian domain. And you see that what I'm left with is essentially the signal only inside the patch I'm interested in. And the coefficients corresponding to that are exactly in 1, 6, 15, and 30, which are the axisymmetric fields I showed you before. So just as a demonstration, I went onto HMI and I got a magnetogram from a sunspot, and I decomposed them, and I reconstructed them, and I took a difference. And it seems to be doing pretty well. And the number of basis functions in this is surprisingly much lesser than what you would need if you constructed it using the plane wave basis. Not only circles, you can make a cat, you can make a Hermitian duck in the spectral space. You can go crazy with these things. So, but again, if only your perturbation is in the shape of a cat, should you use a cat? But in our case, our active, so this is an emerging active region from Birch et al. 2019. And again, I pick up a pencil, I draw a contour, this time sort of keeping in mind that we sort of want divergence v equals 0 within the patch that we wish to explore. And that's what the contour looks like, that's what we reconstruct, and that's the difference, which means that we're sort of explaining everything inside the area of interest. And these are the basis functions. So these are what we would ideally want to infer. And let's say we had a plane wave basis, and this is sort of a before-after picture. So on the left, we have a reconstruction from the plane wave basis. In the middle, we have a Slepian basis. So they, at least on the surface, they look fine. But inversion is not only about getting what you have at the surface, but also what's there in the depth. So if we use plane waves, what we have on the left looks like that. Now, if you have done enough inversions, you would immediately recognize that that's dominated by regularization, because you have this oscillatory pattern in depth. And we don't want that. So that also requires many, many different L curves. But now if we use Slepian functions the way we defined here, that's what it looks like. And that's a far more stable inversion with a single well-defined knee of an L curve. So we go from an unstable inversion to a very stable inversion. And to give like maybe one cool plot here, we go in depth from our inversions on the right. And this is how it sort of looks like. This is still very, very much work in progress for an emerging active region. But as of now, this is what we are seeing. And so we went back 30 hours, and we did some averaging. And this is what it looks like. And we went back then 13 hours, and that's what that looks like. And so we were sort of happy because these are emerging active regions, so they should move up. Chris already showed supergranules, which is done exactly along the same principles of Slepian functions. So that's another demonstration of work in progress. And finally, of course, I've not done all of this alone. And my advisor, Jeroen Trump in Princeton, some of my collaborators, Tuneer and Shravan from TIFR, of course, Chris, Frederick from Princeton, and Prasad and Samarth. And the work on Slepian functions was funded as a part of the Elizabeth H. and Dahlan F.A. Award by the university during the last summer. And with that, I will leave you with a collection of things that I have shown and not shown. So the first row is everything that I've shown you, and the second row is sort of what I have not shown, but that's some side projects that I have done which relates to correcting for differential rotation. Because magnetic fields are very weak signals, and so if you want to resolve a weak signal, you need to ensure that the strongest signals are very well measured and the errors are also very well calculated. So if you have further questions about corrections for differential rotations using full mode coupling treatment, feel free to talk to me. But other than that, I'll take questions.
Thank you very much. Questions? I have one on the Slepian basis for the active regions. There seems to be some arbitrariness on the definition of the boundary of the active region itself.
Yeah.
Is the result dependent on that? How do you define it?
It is, but what we are planning to do is, you draw a certain area which is inspired from what you see on the surface, but then you slowly increase it in size. Because if it's optimally concentrated within a certain patch, if you increase it, it should still be concentrated within that. And so we would see at what point we are inverting for consistent features as we keep on increasing the size of the Slepian functions.
So you expect at some stage that the result will be independent of the
Yes,
size of the
exactly. But the point is, the larger you make it, so the number of Slepian functions that's needed is dependent on the area of this patch. And so the larger you make it, the number of model parameters increase. So we would ideally want to keep it as small as possible without violating any sort of leakage beyond it.
Any other question? Do you expect, maybe with the global modes, do you expect to get something significantly different from the existing? I mean, the theory was extremely interesting and convincing, but
it's hard to say because I don't know if I don't think there has been a formal inversion. It's always been like, you take a toroidal field and you see what it gives you, and you compare that with the observations. So that's not really. It's like a very non-unique process. We are trying to do not a unique but a traditional inversion. So it's hard to say.
Okay.
Yeah. Thank you.
Thank you very much. Thanks, John, again. And the last speaker this afternoon is Paul Bushby.